we want to look at the upper hemisphere of radius A in cylindrical coordinates and look at what we would have to do, say, to integrate and find its volume or its mass or whatever. We want to see how we break this thing down in terms of our polar coordinates by partitioning, etc. Well, let's just start with a little bit of an overview. This stuff in purple is unreadable, but I've kind of repeated it down here. We have the hemisphere, and it's badly drawn. But we have the point r star theta star 0 down in the plane. And our question is, how far do we have to go up to get to the sphere? Okay? So, well, I've drawn without the sphere over the top of it. We understand there's a sphere above this point. And that is true anytime r star is less than a, right? For any r star less than a, there's going to be a point above it on this hemisphere. So we have the point r star theta star. That means it's a distance r star from the origin, and the angle to this line segment here is theta prime, measured again counterclockwise from the positive x-axis. Then again, r star is less than a, so how high up do we have to go to get the sphere? Okay, well, people had a little trouble with this, but all it comes down to is you have a right angle here. Right angle between any line in the plane and a vertical upward line. And this point is directly below. You know, to get the point directly above, you go perpendicular to the plane. So this has to be a right angle. So you have a right angle here, and you also then can these would then form two sides of a right triangle, and that's something you always want to kind of look for. Well, if we draw a side from the origin out to our point on the sphere, we've completed a right triangle. And the right triangle, if we kind of turn it around and look at it straight on, has almost couldn't see the R there, got smudged in movement. Okay, we have our R star. I thought I was seeing an X there. That wasn't what should have been there. Okay, we have our R star here. We have our hypotenuse, which is what? It goes from the origin to our point on the sphere. It's a radius. It has length A. And this is something we've really got to get used to, because this is used again and again. Okay, and then here's our z coordinate corresponding to our r star theta star. So what is that? Z is then a squared minus r star squared. Okay? Now this is what we need in order to describe the sphere in cylindrical coordinates. Okay? Now let's go back up here. The circle that we have in the xy plane down here, the plane perpendicular to the z plane, is characterized by r equals a, right? That's all we need. But of course theta goes from 0 to 2 pi because we go all the way around the circle. So that the points inside the circle are characterized by theta is somewhere between 0 and 2 pi, and r somewhere between 0 and a. So this circular region down here in the plane lies directly under the hemisphere, and for any point r theta down here, we know how to find z, how far we have to go to get up to the sphere. So I haven't, well, yeah, I have. Got a J there that's kind of, yeah, there we go. It was kind of okay, but there's a little blank spot. I'm saying that we can describe our hemisphere then by saying that r goes from 0 to a, theta goes from 0 to 2 pi, and z now we know goes from 0 to the square root of a squared minus r squared. Doesn't depend on what theta is. No matter what theta is, if we're at distance r from the origin down here in the xy plane, we have this triangle, and z is going to be square root of a squared minus r squared. And if r is a coordinate of a sample point r star, then we have this. So there's a description of a hemisphere in terms of inequalities. And this description is going to end up giving us an integral where z goes from 0 to square root of a squared minus r squared. So we integrate from that with respect to z. And from 0 to 2 pi with respect to theta, and from 0 to a with respect to r, except that our volume increment isn't dz, d theta, dr. Okay, so we have to work out what our volume increment is. In x, y, z coordinates, the volume increment would have been delta dx times dy times dz, but that doesn't work out because, as we know, in polar coordinates, the area of a region down here defined by a delta r and a delta theta is r delta theta, which is the arc distance here at our sample point, and our delta r, which is this distance, okay? That's the area of this region down in the plane, okay? And that's something we did the other day, so I think I can count on the fact that you know where to look if you don't completely understand that, okay? Well, that's the area of our typical increment down here, and now we build that up from 0 to the square root of a squared minus ri star squared, okay? And we get the region above this area increment down in the plane, but up to the sphere, or a good approximation to the region if our increments are all small, okay? Well, then, this goes from 0 to what? A squared minus r star squared, okay? But let's do this in detail with a well-written partition so we know where all these i's and j's come from and know what they mean, okay? That's the overview. So what we say is, okay, look, we're going to partition the interval, our interval from 0 to a. So r naught is going to be 0, r1, then r2 up through rn, which is equal to a. And we have a sample point ri star, I didn't write it out before, in the ith interval. And here we have a sample point theta j star, a sample value of theta in the jth interval. And of course, this is the ith r interval, and this is the jth theta interval. Theta, of course, goes from 0 to 2 pi, and there's our partition. Theta goes from theta naught to theta sub m. And then what? Then z goes from where? From 0 up to the sphere. How far up is the sphere? Well, if we have sample point ri star, theta j star, the distance up to the sphere is square root of a squared minus ri star squared. So for these intervals, our z is going to go from here to here. And you know, we say we got p sub I. Z goes from z0 to z p sub I. And that depends on the index of r, okay? So with this sample point, we have this partition, and that corresponds just to one stack from the plane up to the hemisphere. Okay, so this stack now corresponds to ri star, theta j star, z. Well, okay, this stack corresponds to ri star, theta j star. That's what we have here. And that's how we labeled it. The angle's theta j star, we have a delta theta j. We have an ri star that, you know, we have the arrow here, and I never did relabel it, but ri star is the distance from here out to this Ri ring, and a delta R sub I width of the increment, okay? So there's our stack, and here in red is our typical increment, okay? It has sample point zk star, and of course Ri star theta j star. So this is our point, Ri star theta j star zk star, our sample point within this increment. So I call this red increment the increment with sample point Ri star theta j star zk star. There it is. What's the volume of the increment? Well, the base has area Ri star delta theta times Ri, the same thing that we have here. Did I say that right? Ri star delta theta j times delta Ri. That's just what we have here. And then the volume, we multiply the area of the base by the altitude being delta zk. So now the total volume, the approximate total volume, we sum this up over all possible i's, j's, and k's. Okay? We start with the stack. And this first sum, we sum from k equals 1 to p sub I. We take this expression and sum it from k equals 1 to p sub I. That's the typical volume, okay? And then from j equals 1 to m, that gets our thetas, and from I equals 1 to n, that gets our r's. Now I have it written in this order because that's the order it came out when I wrote it up here, but I want to change the order of this expression to match the expressions up with the summations that apply to them, okay? So the only thing that depends on k is our z, our delta z sub k. So we put that over here in our summation with respect to k. Okay, now at that point, we've just got this stack. But then we sum from j equals 1 to m over a delta theta sub j's, okay? And that takes us all the way around the ring, a ring of this width of constant area, or constant distance from the origin, a ring in the xy plane. At every partition of that ring, we have a stack. Okay? So we have a set of stacks around the ring. And then, and that's what we have with this set of parentheses. And then we sum that from I equals 1 to m. And the quantities that depend on I are the Ri star and delta R sub I. And what does that mean? Well, that means we go from the center all the way out to the radius of the sphere in the plane. And we have a stack at every increment. And so what we have, since R has been partitioned into n subintervals, we're going to have n rings. Each ring is going to have a stack. The stacks in the middle are going to be higher than the stacks out at the edge because the sphere is higher above the center than it is out here near the edge. So we're going to have these sets of stacks approximating the area of the sphere. We take the limit by the process that I assume you reviewed and understand, and don't really want to take the time to do rigorously because we have other things we need to focus on. This approaches the integral. And I wrote down something, there's something I didn't write down, there should be an R in here. Okay? So when we take the limit as the increments approach 0, the Ri's become R's, the theta j's become thetas. We no longer have discrete quantities, and we approach this integral in a fairly straightforward manner.